Welcome back to the Deep Dive. I'm your host for today's analysis.
And I'm your expert guide, really excited to dig into this one.
Yeah, me too. So to start off, I want you, the listener, to just completely erase that picture you might have in your head of a typical factory.
Right, the whole old school industrial revolution image.
Exactly. Forget that grayscale footage of a conveyor belt just crawling along, stamping out the exact same widget a million times in a row. That world is, well, it's basically gone.
It really is. I mean, that's the Henry Ford model, right? The whole you can have any color as long as it's black thing. That just doesn't fly anymore.
No, it doesn't. Today, we are stepping into the world of high-mix, high-precision manufacturing.
Which I know sounds like totally dry industry jargon.
It does sound like jargon, but it's actually this crazy high-stakes balancing act. It means a factory needs to produce, say, 5 complex aerospace parts, then immediately switch over to 10 medical implants, and then maybe 3 automotive transmission gears.
And here's the kicker with all that. Every single one of them has to be perfect.
Down to the micron.
Down to the micron. It's a paradox, really. You need the flexibility of a little custom workshop, but you still need the speed and the volume of a massive mass production facility.
Because if you mess up one part in a high mix patch, you haven't just ruined a $5 part. You might have actually scrapped 20% of that entire day's order.
Exactly. The pressure is immense.
It really is. And in preparing for this deep dive, I was reading through our source material today, which is the technical documentation from ISCAR on their advanced tooling.
Yeah.
And I realized something kind of terrifying.
Oh, yeah.
Yeah. The entire modern world, I mean, our planes, our cars, our medical devices, it all hinges on this one tiny, violent point where a tool actually cuts into metal.
Yes. The chip-tool interface.
The interface. It sounds so clinical when you say it like that, but when you look at the actual physics involved, it's a literal inferno in there.
Oh, absolutely. It is an absolute torture chamber for materials.
I mean, we are talking about contact pressures that would crush a submarine. And the localized temperatures are hitting, what, 800 to 1,000 degrees Celsius?
Easily 1,000 degrees.
That is hot enough to turn solid rock into lava.
Yeah.
And we expect this little engineered piece of carbide to just sit inside that volcano, cut through hardened steel, and not deform by even a fraction of a hair's width.
Right, and do it thousands of times in a row. That is the high precision part of the equation we were talking about. If the tool yields to that heat even a tiny bit, the part is out of tolerance. It's garbage.
So that is our mission today. We are going to unpack how engineers at places like ISCAR actually solve this impossible problem.
How do you build a tool that can literally survive hell?
Right. We're going to look at microscopic force fields, modular tools that snap together like Legos, and the digital brains that can predict the future.
It's going to be a pretty wild mix of quantum chemistry and heavy mechanical engineering.
Let's start with the heat. The documentation mentions thermomechanical interactions. Now, I know that basically translates to heat and motion, but break that down for us. What is actually trying to kill the tool inside that cut?
Well, there are 3 main assassins here. The first one is pretty obvious, abrasive wear.
Like friction.
Yeah, exactly. Think of it like taking a piece of sandpaper to a block of wood. But in this case, the sandpaper is hardened steel and you're moving at supersonic speeds. It just physically rubs the tool away.
Okay, that makes sense. Friction equals wear. Simple enough.
But then it gets weirder. The second assassin is adhesive wear. The metal you are cutting gets so hot and so pressurized that it actually becomes sticky.
Sticky metal.
Yeah, it literally welds itself to the cutting tool. Then, as the chip breaks away from the main block, it rips a microscopic chunk of the tool out with it.
So the tool isn't just wearing down smoothly, it's actually being torn apart from the surface.
Exactly, ripped apart bit by bit. But the third one is the most sci-fi concept here. It's called diffusion wear.
Yes. This was the part of the documentation that absolutely blew my mind. Explain what happens here.
Well, at 1,000 degrees Celsius, solid objects don't really act like solid objects anymore. The atomic structure gets highly excited. So the atoms in the cutting tool and the atoms in the metal you are cutting actually start swapping places.
Wait, hold on. You're saying the tool is essentially dissolving into the chip?
On an atomic level, yes. The chemical barrier completely breaks down. The tool loses its identity, basically. It creates this crater on the top of the tool. And once that crater gets big enough snap, the edge just fails.
That is horrifying for an engineer.
Yeah.
So how do you stop atoms from swapping places? The source material introduces this thing called sumo tech.
Great name, honestly.
Sounds like a professional wrestling move. But chemically speaking, what is it?
Sumo tech is basically ISCAR's answer to all that volatility. It's a combination of a very tough core, which is a micrograin carbide substrate, and a highly engineered coating on top.
The force field.
The force field, exactly. But here's the thing. You can't just have one universal force field for everything. ISCAR splits this into two specific disciplines, PVD and CVD.
Right. I saw these acronyms all over the report. Physical vapor deposition and chemical vapor deposition. Why do we need two different ones? Why isn't there just one supercoating?
Because they solve completely different problems. Think of it this way. PVD is a wetsuit, and CVD is a firefighter's turnout gear.
Okay, I really like that analogy.
Yeah.
Let's start with the wetsuit, PVD.
So PVD coatings are deposited in a vacuum, and they are incredibly thin. We are talking nano layers of things like titanium aluminum nitride, and because the coating is so thin, it allows the cutting edge underneath to remain razor sharp.
And why is being sharp the main priority here?
Because of the material you're cutting, PVD is generally used for sticky materials, things like titanium alloys, high-temp superalloys, or austenitic stainless steel.
So this stuff heavily used in aerospace.
Exactly. These materials are gummy. They really want to stick to the tool. If you have a dull edge, the material bunches up, creates massive heat, and you get that adhesive wear we just talked about.
Oh, I see.
Yeah, a sharp PVD-coated edge slices through cleanly. It creates low cutting forces. It basically prevents the whole mess from starting.
So PVD is the slick, sharp wetsuit for the sticky stuff. Now, what about CVD, the firefighter gear?
CVD is for when you are fighting pure heat. These coatings are much thicker, multi-layer structures, and the key ingredient here is usually aluminum oxide.
Which is a ceramic, right?
Correct. It acts as a heavy-duty thermal barrier. When you are machining something like cast iron or plain steel, you aren't as worried about the material sticking. You are much more worried about the sheer volume of heat generated by continuous cutting at high speeds.
Like peeling a potato, but the potato is solid steel and you're peeling it for 20 minutes straight.
And the peeler is glowing red. The CVD coating acts as an insulator. It blocks that intense heat from ever reaching the carbide core.
Because if the heat gets through...
If the heat gets through, the core softens and deforms plastically, almost like warm butter. The CVD shield prevents that, completely stopping that atomic diffusion where we talked about earlier.
So if I'm running a marathon cut on steel, I want the firefighter suit, the CVD. But if I'm doing precision surgery on sticky titanium, I want the wetsuit, the PVD.
That's the perfect way to visualize it.
Okay, so we have theoretically engineered a tool that can survive this atomic blender. But now we run right back into the high mix problem I mentioned at the start of the show. Because it's not just about surviving the cut, it's about managing the logistics of the factory floor.
Right. This is where we transition from material science into industrial economics.
Because if I'm a shop owner, and I have to make 10 totally different parts today, that means I have to physically change the tools on my CNC machine 10 times.
At least 10. Probably way more.
And every single time that machine is stopped to swap a tool, I'm losing money.
You're bleeding money. And it's not just the time it takes an operator to unscrew a bolt. In a traditional setup, when you put a new tool in, you have to requalify it.
Requalify, what does that entail?
You have to teach the machine exactly where the tip of the new tool is. Is it 100 millimeters long? Is it 100.2 millimeters? Because if you are off by a hair, you crash the machine. So you measure it, input the offsets, run a test cut. That whole process can easily take 15 minutes. Do that 10 times a day, and you've just lost over 2 hours of production.
Enter logic quick. The source material presents this modular platform as the ultimate solution to the downtime nightmare.
It's a beautifully simple idea. Leave the main body of the tool clamped in the machine and just swap the cutting head.
Like changing the blade on a disposable razor.
Very similar concept, but the engineering required to make that work in metal cutting is insane. ISCAR highlights this micron-level repeatability.
Which means I can just click a new head on, and the machine already knows exactly where the tip is.
Exactly. No measuring, no offsets. You click it on and you hit the green button. It turns a 15-minute changeover into a 30-second one.
That sounds absolutely fantastic for speed, but I have to play the skeptic here for a second. If I'm just snapping a cutting head onto a body, isn't that connection inherently a weak point? A solid bar of steel is always going to be stronger than two pieces clicked together, right?
In theory, yes. A mechanical joint is usually the first place where vibration starts. And vibration, what machinists call chatter, ruins the surface finish of the part.
So how does the logic quick system not just rattle itself apart when it slams into hardened steel?
It comes down to the mechanical integrity of the connection. They use a specific facial contact combined with a tapered polygon shape.
A tapered polygon. Like a pyramid.
Sort of. Imagine a wedge shape, but with multiple flat sides. As you tighten it down, it pulls the cutting head back against the face of the holder with immense force. It creates this incredibly high torsional stiffness. It actively resists twisting and dynamic deflection, so once it's locked in, it behaves almost exactly like a solid monolithic tool, even with long overhangs.
Wow. So you get the total flexibility of the quick change system, but you don't sacrifice the rigidity you need for a smooth cut.
Precisely. It allows you to run a high mix environment without suffering the high downtime. It also dramatically reduces the tool inventory you have to keep on hand.
Let's pivot to a specific type of cutting that honestly sounds like the most dangerous one of the bunch. Drilling.
Ah, the art of the hole.
The source material makes a really strong point. The drilling is uniquely difficult compared to milling or turning. Why is poking a hole so much harder than just shaving metal off the outside?
Think about the physical environment. When you are milling the outside of a metal block, the chips just fly away. The heat radiates out into the open air.
But when you drill,
You're trapping yourself. You are working inside a closed, blind hole. The heat is trapped. The chips are trapped. If those metal chips don't get out immediately, they pack up inside the flutes of the drill. They jam.
and then what happened?
And then the drill snaps instantly. And now you don't just have a broken tool, you have a broken tool permanently stuck inside a $5,000 aerospace part. It's a total disaster.
So ISCAR has this Logic 3 cam system for drilling. It looks like a hybrid of the modular stuff we just talked about.
It is. It uses that exchangeable tip on a rigid carbide body for flexibility. But the real hero feature here isn't the tip itself, it's the plumbing.
The plumbing.
The internal coolant channels. They are specifically designed to shoot extremely high-pressure coolant straight through the body of the drill, exiting right at the cutting zone at the very bottom of the hole.
So it's basically like pointing a fire hose right at the point of impact.
Exactly, and it does two crucial things. First, it keeps that temperature stabilized so you don't get the diffusion wear. But more importantly, the pressure literally blasts the chips up and out of the hole. It completely evacuates the trap.
The document says this allows for drilling depths exceeding 5 which means 5 times the diameter of the drill.
Which is exceptionally deep for a high-speed production environment. And it means you don't have to do that pecking motion anymore, where you drill a bit, pull out to clear the chips, drill a bit more. You can just plunge straight down reliably.
But I did notice the report also lists solid carbide drill options, like the IC908 and IC948 grades. If the exchangeable head is so fast and runs so cool, why would anyone still die the solid one?
Because sometimes good enough just isn't good enough. If you need a hole that is perfectly mathematically straight or has an incredibly tight tolerance on roundness, a solid carbide rod is still the absolute king.
Because it has 0 joints.
0 joints. It provides absolute maximum torsional strength. So for the highest possible precision, you might sacrifice the quick change modular speed and go for the solid tool. It's all about choosing the right weapon for the specific battle.
Okay, so we've drilled our hole. Now we need to shape the rest of the metal. This brings us to what I like to call the geometry wars.
This is where we look at the actual shape of the cutter itself.
Let's talk about milling first. The document highlights the Healy-Do family of tools.
It refers to a double-sided helical or twisted cutting edge.
Why twist it, though? Why not just have a straight, flat blade hitting the metal?
Imagine diving into a swimming pool. If you do a belly flop, if you hit the water totally flat, what happens?
A huge splash.
Yeah.
A lot of pain. A very red stomach.
Right. That's a straight cutting edge hitting a block of steel. It's a massive shock. It causes huge vibration. Now imagine a perfect Olympic dive. Your fingertips enter first, then your hands, then your arms. You just slide right in.
Ah, that's the helical edge.
Exactly. It creates a gradual entry into the cut. One corner touches first, and the cut travels smoothly along the edge. This suppresses chatter. It distributes the load and stabilizes the tool. It means you can do heavy, roughing-taking, huge, aggressive bites of metal without shaking the entire machine apart.
On the flip side of that, the source discusses fast-feed milling cutters. And the strategy here seems entirely backwards to me. It says the strategy is a shallow depth of cut, but extremely high feed rates.
This is a pure physics hack. It's brilliant.
Thou so.
Usually, when you cut deep into a piece of metal, the resistance pushes back heavily against the side of the tool. This is called radial force. It makes the tool want to bend or deflect away from the cut.
Which is terrible for precision.
Very bad. But fast feed cutters have a highly specific geometry that actually redirects that force. Instead of pushing sideways, it directs the force upwards, actually straight up into the machine's spindle.
And I assume the spindle is strong enough to handle that.
The spindle is the strongest, most rigid part of the entire machine. It can take massive axial loads. So because you aren't bending the tool sideways, you can run the machine at insane speeds. You're taking tiny little nibbles, but you're taking them like a piranha in a feeding frenzy.
So fast feed is all about removing material quickly by hacking the physical force vectors.
Precisely. It minimizes the spindle load. It's totally ideal for things like clearing out deep pockets in a mold or a die.
And then just quickly on turning, the documentation mentions neo-do inserts. These are described as having double-sided negative geometries. Now, why negative? Negative usually implies something bad.
In machining terms, positive means sharp and pointy, kind of like a kitchen knife. Negative means the cutting angle is tilted back to be more supportive. Think of it more like a heavy masonry chisel. You are putting the sheer mass of the carbide directly behind the cutting edge to support it.
So it's a brute force geometry.
It's a tank. It has immense thermal robustness. It's designed specifically for heavy roughing on tough steels and stainless steels, where a sharp, delicate, positive edge would just instantly chip off. And because it's double-sided, you get twice as many cutting edges per insert. So it's a smart economic play as much as a performance one.
So we've got the chemistry with the coatings, the mechanics with the modularity, and the physics with the geometry. But there is one final piece of the puzzle that the source material really emphasizes. The brain of the whole operation.
Digital integration. This is the whole Industry 4.0 aspect.
We hear the phrase digital twin thrown around a lot, but what does it practically mean for the engineer or the operator actually standing at the machine?
It means the absolute end of guesswork. In the old days, if you had a new material, say a brand new alloy of Inconel, you'd look up a chart, take an educated guess at the speed, and run a test part.
And just listen to the sound of it breaking. If it screams, slow it down.
Exactly. But that trial and error phase costs so much money. And if you're making a complex prototype where you only have one single raw billet of metal, you really can't afford to scrap it while you try to dial in the settings on the floor.
So the digital twin allows you to effectively crash the machine virtually instead of in reality.
Yes. You download the exact digital model of the ISCAR tool, the precise geometry, the coding data, everything, and you load it right into your CAM software. The software utilizes its material databases and actually simulates the cut. It predicts the cutting forces, the thermal loads, even the expected wear.
It essentially tells you, hey, if you run it this fast, you're going to melt the tool.
Before you ever touch a piece of real metal, it reduces that trial and error and guarantees process stability from the very first cut.
Let's ground this in reality for a second. Does all this tech, the PVD wetsuit coatings, the twisty helical geometries, the digital brains, does it actually translate to real-world results?
The case studies in the report are incredibly compelling. The aerospace one really stood out to me. They were machining titanium alloys.
Right. The sticky, gummy nightmare stuff.
Exactly. They combined the Sumo tech coatings, that PVD wetsuit, with the milling cutters we talked about. The result was a 40% improvement in total tool life.
40%? That's a massive jump.
It is huge. It means you are buying 40% fewer tools over the year. But more importantly than that, they saw a 20% reduction in actual cycle time. If you are running a factory 24/7, getting 20% more parts out the door every single day is pure profit.
And what about the automotive example they gave?
That was using the Logic 3-cam modular drill on engine and transmission components. The big win there was reliability. The whole quality was totally consistent, the chips didn't jam up, and their overall equipment effectiveness, their OEE, went way up. The whole production line just ran smoother with less intervention.
It's incredibly impressive to see how it all stacks up together. You really can't just have one part of it. The advanced coating needs the tough substrate beneath it, the geometry needs the rigidity of the modular holder, and the whole mechanical system needs the software to tell it exactly what to do.
It's a complete ecosystem. You can't just go out and buy a magic drill and expect miracles if you don't treat the entire process as an interconnected system.
That is definitely the big takeaway for me today. ISCAR isn't really just selling chunks of carbide to factories. They are selling certainty.
And certainty is by far the most valuable commodity in manufacturing right now.
They are providing a technical shortcut, giving you a process that, despite the 1,000-degree heat and the atomic diffusion going on, is entirely predictable.
And that is exactly what lets you tackle that high-mix environment without totally losing your mind.
Here's a final thought to leave you with today. We've talked so much about how much data and deep science is now baked into these cutting tools. Digital twins, atomic-level nanocoatings, force vectoring geometries.
It's a very, very long way from a blacksmith hitting hot metal with a hammer.
It really is. So as these tools become increasingly digitally connected, and as the new alloys we invent become even harder to cut, is the machinist of the future even going to be a machinist? Or are they going to have to be part data scientist, part metallurgist?
The line is definitely blurring. The days of just turning a handle on a manual mill are basically gone in production. It's rapidly becoming a high-tech laboratory out there on the factory floor.
It's something to mull over the next time you look at a car engine or a plane wing, or honestly, even just a simple metal screw. Take a second to imagine the violent, incredibly precise, and scientifically engineered battle that had to happen just to create it. Thanks for joining us on this deep dive.
See you next time.